Alright, hello and welcome to some new slides. These are going to be about a topic called containers. And we'll actually have time to finish these today and even get into some new stuff. Some stuff other than these slides. So look forward to that. I'm excited. So let's talk about these things called containers. They let us put stuff in them. It allows us to store things, and there's a bunch of different containers, so there's a bunch of different ways of storing some stuff. Okay? You already know one. You already know vectors. Okay? So let's generalize that. What does it mean to store some stuff? What is an abstract data type, called an ADT for short, first of all, and then what is a container? Okay, so an ADT, or an abstract data type, it is, well, it's defined with this fancy quote. It's a class of objects whose logical behavior is defined by a set of values and a set of operations, which sounds really vague, but let me break it down for you with a picture. So the idea of an abstract data type is that it's like a black box, okay? It's a class that has been defined for you, but we don't really know how it works. We just know what we can do. We can ask that black box to perform certain operations. So vectors, for example, nobody knows how the standard library has implemented vectors. We never looked. I know, but you never had to know, right? We've treated vectors like a black box, and we've just been able to ask the box to do stuff for us, right? It responds to operations, but we don't really know, and we also don't care how vectors implement stuff. We just say, hey, vector, push back a number, push back 2, and it's like, sure, got you. And then eventually, we ask it again, like, okay, maybe this was the first thing that we pushed. We ask it, okay, hey vector, what's at index 0? And then it should respond with the thing that we pushed back first. It's like, oh yeah, that was 2. So as long as vectors follow these like vector rules, we don't care what's going on inside of this box, right? Vectors, they're just black boxes to us that respond to like pushback, popback, at, size, all that stuff. As long as we get our answer back, it just works out. Okay, a vector, we treat it like a black box. So that's an abstract data type. That's what it means. It's something, it's a class defined by the operations that we perform on it. And then finally, a container is just kind of like a data type that holds things. Okay, it's a type that holds elements of some other type. Okay, you can have containers of containers if you'd like. You can stack them. So vectors, for example, are containers. You can put stuff, you can put ints in a vector, you can put strings in a vector, you could even make vectors hold vectors themselves. A vector of strings, whatever you want. And yeah, there's a bunch of other containers though. Vector is just one kind of container class, we say, okay? Container class, and yeah, a vector is one type of container. Containers are things that hold elements, and the key thing about an abstract data type is we don't know. We don't know, and we don't care about how it's implemented. Okay, so those are just some terms, and now let's talk about vectors again. All right, so what is a vector really? Vectors are a random access container, we say, that can grow. So what does that mean? Random access means that you can have your numbers stored at a given index, okay? So we know index 1, index 2, index 3. You can go straight there. You can go straight to index 2 and get your 4 out. Okay? That's what it means to be random access. You just go straight to index 2. That works out. You can add a new element to the end of a vector with pushback, right? That'll be index 4, whatever you want to put there. So yeah, random access means everything has an index. You can immediately go to that index. There's no waiting. You don't have to go through anybody. And then we like our operations to be very fast, and the word for that in computer science is constant. We would like our operations to take constant time. Okay? A lot of vector operations are, which is super nice. So let me just show you the library. I think I accidentally opened up list first because I thought I was going to talk about lists first, but we're talking about vectors right now. Let's go to the vector class, and let's click on stuff like, okay, the dot size, for example, on a vector. Where did that go? Don't have time to search for it. There we go. So the size operation on a vector, how fast is that? constant complexity. That's as fast as it can be. Okay, so dot size is constant, dot add is constant, dot pushback is constant. You can't do any better than that. Those are very fast operations. Okay, so that's beautiful. And yeah, as you know how to work with vectors. You can use dot at and dot size to move around. And so that is a container class that we know and love already. Okay, but let me talk about now iterators. Okay, because that's the new thing. Let's talk about iterators on a vector. Okay, there are iterators on all of these container classes I'm going to talk about today, so we have to generalize this. So what does it mean to be this thing called an iterator? Okay, let's talk about it. So iterators, they are just a class-based way. It's like a black box that pretends it's iterating through something. So it's like a for loop in essence. It remembers where it is. An iterator is an abstraction over the idea of iteration, let's say. And the way they work, the operations on an iterator, which I'm about to explain, are kind of pointer-like. So everything kind of looks like a pointer. Okay? And you've used iterators already. Just in case you forgot, you've sorted stuff, right? So you've been forced to use v.begin and v.end for your vectors. Those give back iterators. Let's go back to that. So yeah, begin returns an iterator to the beginning of the vector. End returns an iterator to the end of a vector. Interesting. So let's talk about this. So here's v, my vector v. It holds 1, 2, 3, 4. And yeah, if I say I would like a iterator to the beginning of the vector, I will ask it to perform v.begin. And what v.begin returns is something of type iterator. Okay? And this is the real type. It's the iterator type lives within the vector type. So if you have a vector of ints, the iterator that begin gives back is the vector of int : iterator. It's like a qualified type. It's very interesting. So the type of this particular v.begin is vector of int : iterator. It's a very long type, I know. But if I have something of that type, and I say like vector int : iterator it, and I set it to v.begin, in essence what's going on is it is being set to a pointer to the first element. Okay? That's how that works. And then v.end is the flip side. It's an iterator to not the ending element. It's secretly it's an iterator to one past the end. So if you ask for v.end, it's going to essentially point there. So you don't want to ever dereference this. It just tells you when the vector is over. So if you ask for v.end, it'll take you there. And yeah, so therefore you don't want to dereference v.end because they are kind of like pointers. Okay? And you can use them like pointers. You can do pointer arithmetic. You can be like, I would like to dereference it right now, and that will give me the value that it's pointing to. That will give me the 1. I'll write some code for this in a second. And you can also, like, advance. You can use pointer arithmetic on iterators. So you can say it++, and it will now point to element at index 1. Interesting. All right, so yeah, let's have some code that goes into this, but that's, gosh, what do I want to say? Let's just do vectors, not CPP. Might as well do multiple files, at least at the start. So I had a vector of ints, and it was 1, 2, 3, 4. And then I made an iterator to the start of the vector, okay? So I made an iterator, and I'm going to have it point to the starting element. So I'm going to say v.begin. The type of what v.begin returns is vector of int : iterator. And it's always the type of your vector : iterator. it equals v.begin. And so now think of an iterator like a pointer. I can say cout *it, and it will it will go in and get the 1 out. It will dereference where it's currently pointing to. And let me just quickly make a bunch of things. oh man, I'm in the wrong place today, aren't I? So let me do a lot of stuff. We want to be here. I just got so excited I started writing code. So there we go. Now we're in the right place. And so yeah, it gives me the 1. That's beautiful. That's what we wanted. And I can advance that iterator. I could say IT++. And now it points to the next thing. And we never want it to get to the end. That's the idea. So use 2. And so one way of iterating through a vector is using iterators. Here's a way to iterate through the vector using iterators. Here's the idea. Here's what you do. You say for vector of int iterator, I'll just call it IT again, equals v.begin. There's not usually a concept of less than, so we just say we want it to keep iterating until it's equal to v.end. The second it's equal to v.end, we want to stop this loop, and then IT++. Star IT, and then we'll do like space. So this starts at the beginning of the vector. IT keeps going to the next element until it hits the end. And the end is, remember, 1 past the end, so we don't want to print that. That's when we want to stop. And so that's a way to go through the entire vector using this concept called iterators, which are an abstraction over like a pointer. Let's think of it that way. And so this is a very generic, nice thing to have. And secretly, that range-based for loop that I showed you before, that's like the whole for int, I don't know, int I in v with that colon, that is secretly being translated into this loop using iterators. Isn't that cool? So that is food for thought. All right. So yeah, let me show you just secretly how iterators are working for vectors at least. They really are using pointers. So like here's my vector. Let's say it only holds 4 things right now. So 1, 2, 3, 4. I can say v or it equals v.begin, and secretly it's pointing to the very first element of v. So like address 100, this is 104, 108, 112, and then over here would be 116, which doesn't exist. That's v.end. And the second I say IT++, it changes this iterator to now point to address 104, for example. If I say IT++ again in the loop, it changes it to point to this new element. And then if I dereference it, it gives me the 3. If I say IT++ again, it points it to here. I dereference it, it gives me the 4. So like this is me printing them 1, 2, 3, 4 on the same line again, as we did. And then the second I say IT++ one more time, it points to address 116, which is not part of the vector. It's 1 past the end, which is what v.end gives you back. Okay? So that's essentially how it's working. That's how vectors are doing their thing with iterators. Hopefully that doesn't seem too scary, all right? Because this is a common thing among all of the containers. So let's talk about lists now, which are very similar to, or essentially the linked list that we read about in our book and that I talked about briefly. So you might be wondering right now, like, what is the point of iterators? Like, we've gotten by without them so far. Why do we need them now? Why am I teaching them to you? Why are they so important? Especially because they look kind of complicated. The reason is that iterators, at least in the C++ standard library, they're defined to work in the exact same way for very, very different looking containers. Okay, so lists, remember, they look like this in memory. Like if you want to store the list 1, 2, 3, 4, it looks like this. 1, 2, 3 with pointers and nodes. Remember those terms? And there's like a null pointer there. And so lists are completely different from vectors. They are also an abstract data type. They respond to similar commands like push back, pop back, push front, pop front, more so than vectors can do. Like, I don't think you can pop from the front of a vector, right? You can do cooler stuff with lists, but again, this is like a black box. You're not even supposed to think about it being implemented as a linked list, but that's okay. That's what we're going to do. So yeah, you can use lists just like you would use vectors for the most part. Lists are not random access, though, so that's a key difference. So instead of including IOStream, including vector, I'm going to include list. That's the C++ list type. So let's go here. Here's the containers section. I'm going to click list instead. So what is a list? I can click on the constructor for you to see like a good example of it, but this is a bunch of list operations. A bunch of me making lists events. It looks very similar to vector, right? I want to make a list events as opposed to a vector events, and I can push them, pop them in different ways. Isn't that cute? So yeah, let's talk about them. You can, of course, use that same syntax that we've used before, but let me just build it up from scratch. Let's make a list of ints, call it L, and I'll start from nothing. I'll L.push back 3, then 4, and now I'll push front 2, and then 1. So what list should I get back now? What's the order? Think about it. So that's lists. They look very similar, and they're just another container that holds things. They have different operations, slightly different operations. And if I want to go through my lists, what do? I use iterators. Okay, and before I get there, I just want to say that insertion and deletion to the back or to the front of a list is constant time. That's not true for vectors. Let me try and show that to you. Vector, here is, are we even allowed to pop front or pop back in a vector? Not really. Never mind. Yeah, but you can do that in the list. And by the way, push front, for example. Complexity, constant time, as fast as it could be. And again, lists have begin and end. Everything's the same. We can go through a list, even though it looks different under the hood, using iterators. Isn't that very nice? So let's talk about that. So there is no .at for lists because you have to start from the beginning. There's no way to get straight to this node, but there's a way to get there in a roundabout way from the start. Yeah, that's kind of how they roll. And so even though there is no .at for lists, you can still iterate through them in the same way using an iterator. Call it IT as usual. So here's my list. Let's just say it's 1, 2, 3 this time. Easier to draw. You can say IT equals L.begin now. This whole thing is L. And it will point to this first node, which gives me the 1 if I dereference it. Okay? And that's the beauty of it. And so that means, first of all, you can use a range-based for loop to go through the list. You don't even have to think about anything. You say IT++, you can go to the right. You can also say IT ---- to go right back to where you came from. That totally works too. You can also use reverse iterators to go backwards through a list. But yeah, you can say *IT, and right now it'll give back 1 because I put it right back at the start. So you can say *IT, that gives back the current element where you're at in the list, and IT++ moves it to here, for example. Okay? And that's how you can print all the elements that you want. And you can move around in that way. So let me just show you a few quick things about that. So list int iterator IT equals L.begin, and then we're gonna see out *IT. You can use the iterator to change things. You can be like, I don't know, *IT equals 42. That totally works. IT++. What's the next thing? Things like that. They all work. You can say IT ---- to move back. And that'll get you back to the original element. But I guess before I do any of this, let me just show you that range-based for loops work. So for int I in L, it uses iterators secretly, in the style that I showed you for vectors to go through everything, get every int out of the list, and print them. So what is the order of this list in the weird way that I pushed stuff? Oh, sorry, it's lists with an S. Boop. It was 1, 2, 3, 4. Yay. And so the first element at l.begin was the 1. I changed it to 42, and then I went away from it for a second. So I went to point to the 2 now, the next thing in the list. Output the 2, go right back. Now it's a 42, right? And then print that. Okay, so that's why you see the output that you see. But that's lists. It's just another way to add stuff. And then you have different options. You can add things in different ways to our list containers. We don't even have the option of pushing or popping the front in a vector. We do now. And iterators abstract over the nitty-gritty details of this black box, and they let us just go through our container in a standard way. All right, next data type. Let's talk about set. A set lives here in the set library, and it's another way of holding stuff. A set holds a bunch of stuff in a special way. So here are a bunch of different ways to make a set. I'll show you my own way in code in a second. But a set stores unique values of your type T in order. It remembers the order, not in which you added them, but if you were to sort them, it remembers that sorted order. Okay, so for example, think of a set like a cloud, I guess. And if you insert into a set 2, 1, 3, 0, for example, in that order, it's going to be like, all right, 2. All right, you next inserted 1. I'm going to put a 1 there. Remember the sorted order of everything I've seen so far. Next you insert a 3. Okay, it's going to go there. Next you insert a 0. Okay, I'll remember it's going to go there. Okay, so a set stores things in sorted order. It keeps track of all that for you, which is nice. And it knows about these kinds of commands. There's no pushing to the front or the back. There's no concept of front or back. It all keeps itself sorted. So it's just, do you want to insert the thing? How many things do I have with a certain number? Erase. Get rid of something. Okay? So the way it's sorting things, the way it keeps it all sorted, means that it has some work to do when you add and remove stuff. It's not constant anymore. It's called logarithmic time. Okay? So that's still super darn fast. If you have 4 elements and you want to access stuff, it's, well, what is log base 2 of 4? It's about 2 operations to go and get stuff. So it's still a very small number, practically constant for small sizes of sets. But yeah, sets are nice in that they remember the order of their elements. And a nice way to notice that it's using that kind of sorted order is to iterate through it using an iterator or a range-based for loop. And when you output those things in that order, from begin to end, it's all going to be sorted for you. So let's take a look at sets. So yeah, to put something into a set, you say insert. Okay? Keeps track of, hey, is something there, is something not there? So set is what I want to include now, so I can make a set of ints, and I can start it empty, that's fine. I can say s.insert 42, s.insert 3, s.insert 1, s.insert 2. And so when I go through it now, it's going to be in order. You can also output, hey, is something there? s.count, hey, is there a 2 there? If so, it's going to give back, yeah, there is one thing of a 2 in my set. You can say s.count 43, and it won't find it, so it's going to give back 0. It's like true or false, essentially. And then we can iterate through, and I'll do that after I show you this. So yeah, hey, is there a 2? How many 2s are there in my set? It's only ever 1 or 0, so give me a 1, and there are no 43s in my set, so it gives me 0 back. All right, and then we can iterate through. You can use a range-based for loop, or you can use iterators. They are the same thing. So for set of int iterator, it equals s.begin, it is unequal to s.end, it plus, cout star it, and then like a space. And so this will go through the entire set from beginning to end, but for a set, don't mind me just grabbing my fan because it's starting to get hot now, the order is sorted. Isn't that beautiful? It just remembers that sorted order for you, and it does it as fast as it can with this kind of logarithmic time. Okay? That's the idea. So sets know the order of their elements. And then I think the last container that I'd like to show you, the last main one, is called map. So there's a map type, and what maps do is just like a set, they kind of store things in a sorted-ish order, but instead of holding a single value, they store pairs of things, pairs of values. So there's always a key value, we say, and a value type. There's a key type and a value type. That's what we use as terms. And so it's kind of like a lookup table. A map, we say, maps keys to values. So a nice thing that a map is good for example, is like storing a phone book. What is a phone book but a way to go from strings? Like you give me a string, like somebody's full name, and then I give you back their phone number. That's what a phone book does. So keys are strings, values are ints. That's how we say that. Okay? So here's what a map would do if I were to insert things into it. It'd be like, all right, associate the key Lawton with the value, whatever my phone number is. We'll just store that as an int. But it stores these pair, okay? This pair of things. And that is what it remembers. And then maybe if I gave my cat a phone number, I could put his name in the phone book. 1235 or something. And so the first thing is the key. That's what you look up in the map. And then the second thing is the value, the thing that you get out when you look that thing up, when you look up that key. There's a mapping going on. Keys are mapped to values, and that's the fancy mathematical notation. That's what's going on there. Okay? So given a key, you can look up the associated value in your map. Let me show this to you. And so because there's those two types involved, and they could be anything, a map takes two little parameters within those angle brackets, within that less than and greater than. It's like, what's the type of the key, comma, what's the type of the value, which is new. So how do maps work? Here's how you can make some of them out of existing things, but I'll show you the maps do have insert, but usually you use something else to just insert the pair of key value things all at once. You use in place. That's the cooler way to do it. So you in place the key value pair. So you have your map, and you say in place the key to the value. You map it. Okay? That's what we're going to do. And so let me show this to you. Dun dun dun. I guess I'll just do this exact example. So map is the name of the container class, and therefore the little header that I want to include, and then I will make my map now. A map from, let's make it a phone book, so I need strings as well. Map from strings to ints, and I'll call it phone book. It'll start out empty, and then I can put stuff in it. I could put mappings into it. Phone book dot in place, so associate a key to a value, so my name to a phone number. My cat's name to a phone number. Yeah, and so now this is my map, and I can look stuff up, okay? Because they map those keys to values. You can say, all right, phone book, what's the value associated with Lawton, the key Lawton? So you can look up somebody's phone number this way. It's like, oh yes, I was associating that key with this number. And so it gives it back to you. And you can see if something is in the phone book, like, hey, is Lonzo in the phone book? You can count. That's what count is for. Is there an entry in the phone book for Alonzo? Like, yes, the count is 1. It's not 0. If somebody is not in the phone book, like, I don't know, maybe my mom's number is not in the phone book right now, then the count will be 0. And that's how you can tell, like, is it okay to go with the .at and look something up? But that is maps. That's what you can do. That's the normal stuff for a map. It's associating keys to values. So a phone book is a great example. And maps are just as fast as sets. They are logarithmic time to do that insertion, that looking up, because how does it like remember like the number associated with lot? And it really is kind of making a phone book deep down inside of its cloud, inside of its black box. It's storing things in order so that it can look it up fast. Okay? You can do that kind of binary search essentially because things are in sorted order. That's why we end up with logarithms. Let's see here. Yeah, let's do iterators now. So maps iterators. Those look a bit weird, so let's see that. So for map string int iterator it equals phonebook dot begin, it is unequal to phonebook dot end it plus plus. And now the idea is star it doesn't really make sense because I can go inside of my phone book and I can get something, but that something is a pair of things, isn't it? It's not just one thing at a time that I can just immediately print out. That is the new thing. So if I look up the documentation for the iterator is a pointer to a pair, and that pair has a first and second entry. Okay, so we can dereference and then get the first, dereference and then get the second. And so usually we use that arrow operator for that. But yeah, it's a pair of things. So you can't just say star it and expect it to like print properly. Now we have it first and it second, because it's a pair of things. It's the key and the value. So we can output the key first, it first. We can be like, oh, that maps to it second. And it's going to print out the mapping for us now. It's like, oh yes, I'm associating Lawton with this number and Lonzo with this number. That's how you can look it up. It knows the answer. Okay, so that's maps for you in a nutshell. I just wanted to give you a taste of all these containers because we're going to be talking about them in detail in CSCI 41 if you take that class. And we're going to get into the nitty-gritty details. We're going to know how these are all implemented deep down. But now at least you've seen them once. So that's containers. And then before we go, before I switch slides on you, let me give you an example here for you to think about. Like maybe some of these containers are better than others for certain situations. Okay, so try and figure out. Here are 4 answers or 4 questions. Try to associate one of these containers that we talked about today to each of these questions. Like what is the best container to hold Pokemon cards and their selling prices? What is the best container to hold a bunch of students on a class roster? Okay, think about that. And there are multiple right answers. There's not necessarily just one right answer. Whichever one you think is best is the one that works for you. Depends on the use case, I guess. Okay? So, Pokemon cards and their selling prices. I would probably say map for that, for example, because you can associate the card name, like Pikachu, to a price. So it's a string to an int all over again, or a string to a double, because you have decimals for prices. So I think maps are the best way to go there. But you could also just store a vector of pairs, right? A vector of Pokemon card name, price, a set of pairs, a list of pairs. But I'd probably go with map. A group of people waiting in line, it really depends. You need order, right? You need definitely order for those people, so I think vector or list would be the right way to go. Sets and maps, they don't really keep track of order very well. Students on a class roster. Again, this is depending on what you're going to do. If you're just going to call out their names, maybe you want them to be in sorted order, so a set would be okay. Or just a vector in general. A vector or a list is fine if you just want to iterate through it, but depending on what you're going to do with this roster, like maybe you can make a map of students' name to were they here today, if you're going to use attendance on that roster. Something like that. So you have options depending on what you want to do. The last 100 days of Bitcoin prices, I think you'd want to be able to quickly look up like what happened 10 days ago. So a vector would be nice because you can immediately go to an index, or you can map a date, like you can have a date type to the price, and so maybe a map would work as well. So there's different options. There's plenty of ways to go here, but I want to get you thinking about these differences. Like what can you do with these that you can't do with others? Like which container is maybe the best container? All right. So that is everything that I wanted to say about containers. Let's see how we're doing on time. Not too horrible. And now what I want to do next is talk to you about the very last topics before we start reviewing stuff in this class. This is the last set of slides before the review. And this is the last new stuff then. And I titled it Beyond C++. I promise to not test you on anything in these slides. This is just for like your information, because you might transfer somewhere that will have expected you to have learned Java. You might transfer somewhere that will have expected you to have learned Python. Some, depending on the school, they teach their first language with one of those maybe instead of C++. C++ tends to be the most common one though, so that's why we use it here. But I'm going to teach you a little bit of Java. I'm going to teach you a little bit of Python so that you can hang whenever you get to your 4-year college. Okay? So that is the idea. That's why we're going to do this. And I promise not to test you on it though. Okay? So let's first talk about Java. What is Java all about? I'm just going to give you a sneak peek. I can't do very much in 2 lectures, I promise. To do as much as I can though. But if you'd like to look more, I can talk to you about where to look. This is a great place, though. This is a great little document. It's a little quick guide to what Java is all about. It's very similar to C++, by the way. Java and C++, they got popular around the same time-ish. And they're both, therefore, they're all object-oriented. They're all about classes. And it should be very similar. Okay, so look forward to that. But I want to, in our time left for this lecture, just give you a little flavor of what Java is all about. Okay, let me give you the Hello World example of Java. All right, so to the code. Let's make a new file called something .java. The extension for Java programs is .java, not .cpp anymore. So usually it's all about capitals and camel case in Java, so let's say Hello World, capitals like that, .java. That's the name of the file. All right? And then Java programs are very picky. They are all about classes. All right? So even if I just want to print Hello World, I need to make a class called Hello World. All right? So the public class inside hello world.java needs to be called Hello World. That's very weird. That's the first thing that I wanted to say. So let's put it here. Then to compile, we're going to say not G++ anymore. That's the C++ compiler. There's a Java compiler, so Java C. We're going to give it hello world.java. Okay? So let's just get that working. All right? So because I named the file hello world.java, Java is very picky. I have to say public class hello world. That's the name of the public class inside of this file. Every file has a class associated with it. This is this one. All right, it's forced to do that. And then I say, for the main function, I put it inside of the class, public static void main string bracket bracket args. You always have to have this. And then there is no return 0 because the main function in Java is void. I can immediately print, and here's the printing. System.out.println, println, hello, comma world, exclamation point, new line. But actually I don't need the new line because it prints and then adds the new line for me. So that's nice. Again, a semicolon. So this is the hello world in Java. And let me type a lot of things now. All right, so first of all, in Java, everything is a class. All right? If you just want a function, like main, you still need to put it inside of a class. Hello World is the name of the class associated with this file. It is a public class. All right, remember the difference between public and private? Hello World is public, so it's visible to the outside world, to the compiler, to everybody. That means other people could use it if they wanted to. And the way to include something in Java, it's called import. Instead of include, we say import. So other people could import it. So this file, because our public class that we're giving to the world is called Hello World, this file must be called hello world.java. It's forced to do that. It will not compile if I made this name of the class anything different. I put some, like if I put a 0 here, it's not going to compile if I say java c hello world.java. It's like, nope. It should be declared in a file name hello world0.java. Silly person. So that's what we're forced to do. And yeah, to compile is java c, name of the file. A lot simpler than G++. And then here's the main function. Okay, let's talk about it. So the main function lives inside the public class associated with this file. If you want to have a main function, that's where you put it. You have to give it this exact syntax. It's public static void main string bracket bracket args. You cannot deviate from that. You must use the definition below. You always get the command line arguments, even if you don't want to use them. Args are the command line arguments, even if you're not using them. Okay? And, alright, so that's nice. It's called main. We're taking the command line arguments as an array of strings. Okay? So that's how it works in Java. In Java, args is an array of strings. Their string type is a capital S. Main is a public method, surprisingly. It's a method of a class rather than just a normal function. Main is a public method inside the hello world class. That's another weird thing. Main is also static, which kind of means like that's what it really is, a function. It's not really a method. That's what static is good for. And it's also static. So every static method belongs to the class. There's only one copy of it. It doesn't go inside of every object, for example. So main belongs to hello world, not any object of the hello world class, which is maybe not something that our book hit too hard on. This also exists in C++, but it's a bit of a weird topic, but this is what I want to say to us now. So, which means that it belongs to the class itself, rather than to any object of the class. And then finally, the key new final difference of Java to C++ is there is no such thing as a declaration of a function of a class. You just start implementing. You put braces. There's no it can find things if they're implemented above or below. Java's cool like that. So you don't have to declare any functions / methods in Java in any separate place. It just finds them no matter what order you put them in. So you just start giving the implementation with your braces. Okay? So that's hello world, the class, with the main static method inside of it, which is essentially our main function. That's why the types are what they are. And let's compile it. Java C hello world.java. That creates a file called hello world.class. Okay? It took us a while, but we got there. And so yeah, because I had this file, I was forced to say public class hello world. That is forced to be the public class in this Java file. All right. So Java C made hello world.class, and then if I wanted to run that file, I can't use the / because Java's a bit different. I say Java itself. So Java, please run my compiled program. And you don't even have to say .class. It knows to look for that. Right? So you say Java hello world, and that runs the hello world.class file, starting at the main method. Yay! So that's our hello world. We did it. That's the first program. And you can look up like what's going on here. It's a very weird library function that we had to call this. Like this is their printing. It lives in the system library, it lives in the out library within that, and that's where the print line, technically a static method, is defined. Okay? Think of it as a function though. And it takes a string you want to print and puts a new line after it. But you can look at all the documentation. It's all online in a very nice place. Java's really nice in that regard. And so let's find system.out.println print line. It lives in java.lang. That's the first place that it's in. And then it's in system. System. It's a system class. Then the out class, the out field. That's the standard output. And then every out object, the out object inside of this class, where is it? Boop. The out is a print stream, and so we can use print stream methods. And one of those methods is print line. And we gave it a string. Boop. So we called this version of the method. And that was our printing call. Okay, so there are a lot of stuff in Java. The standard library of Java is huge compared to C++, and so that's why you have to qualify it like this. Okay, so that is our first program. Please yell at me if you have any questions, but again, it's new, it's slightly different. And I guess the last thing that I want to show you today is just a little bit more Java, like some slight differences like to what we know in C++. But a lot of it's very similar. So the first thing we need to notice is pretty much everything in Java is a class. There are some basic types like ints and doubles, but that's about it. And there are no pointers. That's another interesting thing. And then arrays look a bit different. Like this is not how we use arrays, right? In C++, it looks not like that. So the syntax is slightly off. So let me make a new file with some examples of all this stuff. So I want to call this file, let's call it, I don't know, more Java. More Java.java. And naturally, if that's the name of the file, the public class inside of it needs to be called more Java. And if I want to have a main function, it needs to be called public static void main string array args. Yay. Okay, so let's have some ints. Ints exist in Java, int x equals 42, that's all the same. Cool. You can have doubles, double y, 2.14. Bools are called booleans with the EAN in Java. So it's boolean b equals true. That's all the same syntax though other than that type. Strings have a capital S. And that's the one difference there, and there's no extra library, it's just already included for you. Arrays, again, look a bit weird, so maybe I should be saying this first. Every array in Java is on the heap. So you have to say new in order to make an array. So here's an array of ints, for example. Int, bracket, bracket, that's where you put them in Java. Int, bracket, bracket, r equals new int, bracket, bracket. And you can immediately give the values as well. It's like, put 1, 2, and 3 in it, please. That's how you can do it. So arrays must all be made on the heap. And the bracket bracket goes after the type instead of the name of it. And so that's the array. You can access it as normal. You can iterate through it for int I equals 0, I is less than. Ooh, another cool thing. All arrays know their length. You just say r.length. They all know their size. So go from 0 to r.size, or sorry, r.length, excuse me. And it's not a method, it's just like a variable. It's a field of the array, because it's secretly a class, kind of. And then I++. So this is all the same. But if I want to print this, it's got to be system.out.println, then r of I. Okay? And then, even though I made this array on the heap, I don't need to call delete. And I'll get into that in a second. So here is, I don't know, here's the file, java c more java.java. So that compiles it, makes more java.class. To run it, I say java more java. And then it ran my code, which just did this part. Okay, so here's a bunch of types that are slightly similar. Let's talk about what's going on here a little bit more, and that'll be it for the day. So, okay, first of all, Java runs on what's called a virtual machine, which is weird, but also kind of cool. So when you compile something in Java, that's the reason you can't use the / to just go and run it. Compiled Java programs have to be run on this Java virtual machine thing, okay? But the upside of that is that once you compile a program on your computer, it can run on anybody's computer or phone or anything. It doesn't matter. So that's very different to C++. C++, once you compile it, it can run, but only on the same operating system / CPU architecture combo. If you compile something on an Intel processor, you can't run it on your phone's ARM processor if it's C++. But if it's Java, it will work because it has this intermediate language. The compiled language isn't yet machine code. Okay? So here's my more Java .java. That's the normal file. That's the code, public class. ... Then you use Java-C to compile this to what's called Java bytecode. So more Java .class, and that is ones and zeros. It's a binary encoding of this program. It's a bit closer to lower level, to the machine code, but it's called bytecode. And then you have to run that not on your computer, but you got to give it to a nice black box called the JVM. That's called the Java Virtual Machine. That's what it's short for. Java Virtual Machine. So it's capable of parsing this .class file and making the final code that's going to run on your CPU. Okay? So it runs the code for you. That's how it works. Okay? So that's Java. It's a bit different to C++, but still almost as fast. And then finally, Java is what's called garbage collection, or garbage collected, which is why we teach it. Why we teach C++ to you, because Java lets you get away with some stuff. So in Java, you just say new. You just say new, make something on the heap, and it notices when you're done with that thing. It calls delete automatically for you, which is lovely, but not when you're first learning how to manage memory. Okay, so that's why we teach you C++ here. We gotta force you to learn when to delete things. So, but Java, it deletes things for you. So this array that was made on the heap, it's going to go away right at the end of main. It's like, all right, I know you don't need me anymore, so I'm going to delete myself. It's lovely. No delete is necessary. I guess technically it would be delete bracket bracket because it's an array. Java takes care of deletion for you. All right. So it realizes, it notices when we're finished with stuff on the heap, so like heap memory, let's say, and it garbage collects it, which is lovely. So that's Java for you. So that's the first taste of Java that I wanted to give you today. This is all that we have time for, and next time I'll do some fancier stuff in Java. We'll learn a bit more about it, and then we'll also learn some Python. Okay, so that'll be the last new information in this class before the week before finals, which will be just review. All right, so I'll see you in the next lecture.